So hello everyone, my name is Diego, this is David. So we are presenting our project today. It's based on the concept of the spectral bias that deep learning algorithms have, in particular gradient descent. So let me start reminding you what we mentioned in our previous presentation, because this is basically an extension of the presentation. So originally we had this story of we have some space of functions, and then in this space of functions we have some hypothesis class, and we have a target function that we want to learn, f star. And then we have a family of models. The family of models can represent some subset of functions inside the set. And then we are going to receive some set of examples, the scene examples, and they're going to define some set of interpolators. And then we are going to use some algorithm over this set of models. And this one is going to find some of these interpolators. We can assume that since we have like large enough models, we can perfectly represent this in the given data. And what we had is that among these interpolators that a model can represent, there will be some subset that the algorithm will prefer. And in particular, we saw that in the case of Boolean functions and polynomial functions under some regimes, this was a specific set called the minimum degree interpolators. And this happening to particular settings or learning regimes. So the first one we mentioned was something called sparse target regime. And this consisted in, we have some model, this model has some parameters, and they're initialized randomly in this fashion, following some Gaussian distribution, mean zero, and a variance of 1 over d, where d is the input size. And then we have this for all parameters, and this capital P is the number of parameters. In this regime, we take the limit of P and also n, when n is the number of examples given. And then we assume as well that the target function that we try to learn is a constant sparse, meaning that we are taking the limit of the input size to infinity, but the number of features of this input.
Something is off with the sound. I don't know, like sometimes the sound is just cut off. It's maybe the computer is too far, or maybe it's doing some filtering or something. I don't know.
Maybe it wants to upload your sound also, because you have some background noise. Maybe you can, I don't know.
Okay.
Maybe maybe you can mute yourself, and because it's getting some
Okay.
Let's see if it's better.
I mute myself. Let's see whether that works.
Yeah.
Yeah, it's gone. Cool. Okay. Okay. Yes. So yes, and then the models that we consider were some models called random features, and then we consider this for Boolean functions and using gradient descent. And then we had another regime which was called small features. And then it was similar. The difference is that now the variance is with respect to some parameter that is independent of the input size, epsilon. And then in this case, we also take the limit of the number of parameters and of the noise, but this noise goes to 0. And then in this case, f star is arbitrary, and the as well. So the input side doesn't need to go to infinity for the things to apply. And we consider the same type of models, random features. In this case, we consider both Boolean and real valued polynomial. And then the conclusion that we saw from these two regimes is that when we consider all of these properties, we have the mean degree bias, meaning that the models that we are going to, that the algorithm is going to prefer is those for which the polynomials have the lowest possible degree profile. And the same happened in this case. And then after that, these papers show that this minimum degree bias breaks when we consider other settings. For example, when we had random features with real valued polynomials. But when we consider this setting as opposed to this setting, they also have some empirical results in which transformers show for Boolean the same mean degree bias. But once we consider something else like polynomials, transformers fail. Fail in the sense of they don't present the same minimum degree bias. This begs the question of why is this happening? Why in some settings it happens that there's some mean degree bias, why in others it doesn't? How general can we expect this framework to be? When does it apply to transformers or not? And so we consider that it would be interesting to explore in the literature what explanations were there for this phenomenon. So this essentially defines our project and is trying to understand when should we expect this to apply. So this is essentially a project statement. Now I will jump straight to the results for the sake of brevity and also to motivate a little bit what comes afterwards. Any questions so far? Cool. So to summarize, what are the conclusions or results that we found in our review? So the first one is that the previous two regimes that I mentioned are actually are variations of another well-studied regime called the NTK regime. Where NTK means neural tangent kernel. So for now, I will just briefly mention what is the idea of this regime, comparing it with the previous ones. But later on, we will go into more detail into what this is. So in this case, we will have that the parameters are going to be ordered in some layers. They're also going to be sampled from some Gaussian distribution with mean zero, and their variance is going to depend on the number of parameters in that particular layer. And then we have that the learning rate is going to be lower than some threshold limit for the learning rate. So we can see that this is essentially going to translate to the same parameter 1 over d or epsilon, and we are going to take the limit as well for e, which is the sum of all these n sub l for all layers. And something particular about this regime is the following. We will have two specific characteristics that define this regime. One is that our approximators or models, given some parameters, can be expressed as linear regression. Meaning that there are going to be some features, phi sub x, that multiply with the change in the parameters are going to represent the outputs. So essentially, we want this to be the same as the output of the targets. And this limit, essentially, the function is going to be approximated by a combination of all these modes or features. So, in essence, in this regime, one can show that these features exist, and also there's going to exist a linear operator. You can think of that as a matrix that is called the neural tangent kernel, which is going to be some function of the features. We will define this better, but this is just to give you an idea. Okay, so this is the first part, and then the second part is I guess our main result is that we will see that gradient descent is going to have some bias, and this bias can be represented by a constraint optimization problem, where we're trying to minimize this quantity. I will explain in a moment.
Sorry.
Yep.
Here, the setting is like the first one or the second one? I mean, the epsilon is going to 0, or the number of samples is going to be in this paper.
I guess there's no, we haven't done any exact connection to those two. So for now, I'm just mentioning that there are variations, as in they have the same flavor, but I think that they're equivalent because
when you have a lot of samples.
No, like in the case of for example, when you have this infinitely large number of inputs, and only a fixed subset of them actually is like matters to the interpolation, you could probably use the other ones with weights to result in a bias. So I think those actually don't add anything. But we haven't formally done anything about this.
Okay.
Yeah. Okay. So we'll see that gradient descent is essentially solving this optimization problem, which is a sum of square weights, or this lambda case, which are eigenvalues of this matrix, the kernel operator, such that we are using the eigenvectors of the same matrix. We are linearly combining them with the weights. So we are weighting each of the eigenvectors of this matrix to interpolate the solution. And then if you see, these weights are going to be weighted by the eigenvalues, by the inverse of the eigenvalues, meaning that since we are trying to minimize, we are going to prefer those eigenvectors with largest eigenvalue. So gradient descent has a bias, a spectral bias, to combine just the subset of eigenvectors with largest eigenvalues.
Right.
So this is going to translate to less energy or lower degree. In particular, one of the papers shows that these functions that we, in the Boolean case, we had these parity functions. So if you remember, these parity functions are defined over a subset of the indices. And then one of the papers that we review show that these are actually eigenvectors of the neural tangent kernel, and in particular that the corresponding eigenvalues only depend on the size and have order d to the power of the minus size, meaning that they are quickly increasing, and then this translates into just choosing those with small sizes, which is equivalent to the minimum degree bias. So the result is essentially that this minimum degree bias is just a special case of the spectral bias. And this is actually very general. This NTK regime actually applies to essentially any deep learning model. So this neural tangent kernel can be found for recurrent neural networks, networks that use attention, NLPs. And actually there exists an algorithm so that if you give the architecture, it can output the corresponding kernel. This is something called tensor program, and there's a proof that for this, the neural tangent kernel regime always applies, meaning that this result that gradient descent has a spectral bias applied to basically all architectures that we know in deep learning. Yes. Yeah.
Just to clarify Alariza's question too, so the two settings you showed in the beginning, those are like now, you're saying special cases of the spectral
Yes.
bias, okay.
Yes. So actually, it's not like something is breaking, it's just that the spectral bias doesn't translate in that case into the minimum degree bias, because these eigenvectors don't necessarily have lower degree. It's just that once you fix the architecture, that's going to choose some modes that have lower energy, and those are the preferred ones. And they are not necessarily these polynomials with low degree. Yeah, and so in essence, if we would like to understand what are the bias that transformers have, it makes sense to analyze the NTK for the transformer. This is what we wanted to do, but we couldn't get to that point. At least we found this interesting finding, which is basically answering the question that we started with, which is why does this MD bias break? So with these results, now we're going to derive this if we have enough time. And for that, we're going to introduce the concepts and in more detail what is this NTK framework, and then the derivation. Ciao.
Yeah, just very high level. It's kind of a bit, I don't know, strange, isn't it? Because this NTK business is ultimately linear, and then we're trying to explain deep learning, and so there's nothing deep here.
Yeah.
So it's almost like we are trying to defeat ourselves. If we wanted to explain deep learning has to be doing something different than what is being described here.
Yes. So just a lot of
why
people,
are we doing this?
Yes, so a lot of people point that that's an issue with this framework, and is that they are assuming this kind of non-standard initialization of the parameters.
Right.
Because they assume that the learning rate is very, very, very tiny.
And what would be the more standard initialization, by the way?
I think that this learning rate depends on the eigenvalues of
Sure, but like besides the learning rate, the initialization,
We
the
also
parameter
scale
initialization.
we also scale the parameters by 1 by the number of neurons, so that like when we take the limit, like the activations and gradients don't diverge. So we divide all the parameters by 1 by d, like 1 by NL.
Yeah, the beginning I couldn't hear because I was not muted. So go again.
Yeah, like one more like initialization is we divide the all the parameters in the layers by 1 by d. Like d is the width of the layer, so that is one extra condition that NTK requires.
But people do that in deep learning, or maybe it's like 1 over the square root of the number of parameters.
Yeah.
It's square root, right? Like this is the tiny initialization, and the normal would be 1 over square root or something. Because you still want to have some normalization going. If you have lots of inputs, then you don't want the initial like uncontrolled signal to be really large, because then there will be no learning. You're going to be frozen.
Yeah.
So that's the difference.
The difference is the scale. Like
Right.
essentially, you're making sure that the step sizes are so small compared to the starting point. That is like you're not really moving.
But it still kind of learns, right? Like,
Yes,
but it learns.
but that's because it's
Yeah.
assuming that you have enough features.
Right.
And so
Right.
people have
Yeah.
explored what happens outside of this, and they call this the rich feature regime, whereas this is
Okay.
called the lazy regime. Yeah.
So
the-
we are kind of like saying deep learning, but if it's doing something clever, it's doing something other than this.
Yeah. Uh-huh.
Yeah. Still, it's kind of interesting to understand that, like, it's like, it's a pathological kind of edge case for what neural networks could be doing if they were slightly misused or used differently, right? Like you initialize them smaller, and then you take the learning rate to be smaller, and they might end up doing this. People don't do this in practice because it doesn't lead to better results, I guess. Well, I guess for LLMs, it's very complicated. Like learning these schedules and yeah, other very complicated things that no one understands. But okay, great, thank you.
Cool. Any question?
Yeah, so let's briefly look at what the NTK framework is and how can we use that to analyze the transformers. Suppose you have like a parameterized function or a new number and you want to train it using gradient descent, and we minimize this loss where f star is the true labels. So we want to find theta such that it minimizes this. The way we do that is we sample some initial parameters from some distribution and we make these updates to theta. Where L is this loss function, and here theta is a random variable because we are sampling from some distribution, and all of these theta or t depends on like theta naught. Now this is we are learning the parameters in the parameter space. So here theta is some it lies in some p-dimensional space where p is all the parameter. And each theta will correspond to some function in our function class, and let f be the mapping that takes a theta and gives the hypothesis function in this class. And in the parameter space, we have some loss function which will, for each theta, it will output a scalar. And we can have analogous cost function in the function space. Now it turns out that in the NTK regime, like when we take the width very large and also the learning rates are small, the weight changes very slowly, and we can do some first order approximation, and we can write the changes in the function space as this. So I have to take this one. So C is the cost function, and this is some matrix where this gradient with respect to this matrix or kernel is defined as follows. So x is sampled from x prime is sampled from data set, and this is the definition of this gradient, where we multiply the gradient with some kernel function. So what the and this particular kernel turns out to be this. So it's dot product between these two gradients. So a kernel typically will be like a dot product of two feature maps, like feature map of two inputs, and in this case the feature map turns out to be this gradient. So what the NTK result from this paper says is that as we take this width to infinity, this theta naught becomes a deterministic matrix, and this is called as the NTK kernel. And what the implication of this is that doing gradient descent in the parameter space is same as doing or equivalent to doing kernel regression in the function space, which means that we can now have a closed form solution, and we can analyze this NTK matrix to see what kind of solutions we get. and that will help us to analyze the biases that this algorithms have. Now, this original result was only for MLP and I think this paper, Young et al. In 2021, said that it's true for any architecture, including transformers, and these people derived the NTK kernel for transformers, which can be useful to understand the biases. I'll probably skip writing in interest of time. So.
Wait, I do have a question about this though. It's like the transformer NTK cutoff. Like how complicated it is. Like how does it look like?
Okay, I can write
Like
it down.
is it for multiple layers or single layer or?
I think it's for single layer.
Yes, this one is single
Yeah, single
layer,
layer.
and it's assuming that
Okay.
only the last layer has trainable parameters.
Yeah.
Alright.
So actually, this NTK corresponds to something called the conjugate kernel.
Is it? Yeah, it's something that's recognizable.
As in-
Like I know that for. Sorry, yeah, I know that for example in the MLP case, the NTK kernel is going to be how is this architecture space called modern kernels, right? They come out, which is like a big thing in the study of smooth functions. So in this case, is it a known kernel that comes out or something new?
They have an expression for it.
Yeah.
They have an expression for it. It's a bit lengthy. I can write it down if you want.
Or you can just tell me.
Okay, it's like there are a lot of terms in this. Like, I don't think I can read that out.
But I had a much simpler question. Is this something that mathematicians would recognize it like, oh, I know this guy?
I don't know.
You don't think so?
Maybe it is
It
composed
took people a while to figure out that even for MLPs, it's a known kernel because you can write the kernel in many different forms.
Uh-huh.
And some, like it's not obvious that they are like equivalent or they are the same.
Mhm. In the MLP case, in the first layer, the NTK considers inner products between the inputs. In this case, you will have also products, but now between the embeddings of the tokens. So you have like X transpose, and actually they are not inner products; they are more like outer products, and that's what makes it different. So it's more complicated in that sense, and that's why it's not clear what are the eigenvectors of that kernel.
Okay. All right. Thanks.
There was
Yeah.
Oh, I just wanted to clarify. I think I missed something. Could you say again what C is?
C is some cost function, like similar to L. I guess essentially this. But instead of theta, we just write it in the function space.
Okay.
there was. Okay. So, I guess now what I want to do is to first show that. So I want to first show that gradient descent has its bias can be represented as solving this optimization problem, where it's trying to minimize the norm of the vector parameter, and is going to satisfy this set of constraints that are linear. And then I want to show that this first can actually be translated into this spectral form, which is what we concluded before. So for this, so let this be your training set. Then we have that this cost function that we mentioned before is going to be the empirical version. So it's the sum of these square errors between the model and the target function. Okay, so first let us calculate the gradient, because we're using gradient descent, so we want to know what are the dynamics in this case. So the gradient of the loss are going to be the same as the gradient over this composition of functions that Bowis mentioned. This is already at some time t. By chain rule, this is the same as essentially the derivative with respect to this cost function multiplying the gradient with respect to the map that maps from parameters to functions. Okay. And then we are assuming in this case these squares, and then we can just calculate the gradient with respect to this. This is just 2 cancels 1/2, and then we just get the linear term. Let's call this y. Here, this depends on the parameters, and then we have gradient term. Okay. I essentially did nothing. I just calculated the gradient, and it is just the sum of each of the gradients with respect to the architecture that we're using, and then this gradient in the NTK regime is going to be essentially these features. And what is relevant of these features is that they are constant in the regime. Okay, so since we have gradient descent, that means we are assigning to the parameters at some iteration t+1, the ones in the previous step, minus this gradient, right? And then this is going to be some turning rate. Okay. just algebra. Now, the important step is that this same equation applies to the parameters at time step t, which means we can replace the same terms, and we can do it multiple times until we get to theta 0. Right? And this is going to be some sum of terms. So what is important to notice here is that we're saying that the parameters can be expressed, or the change in the parameters can be expressed as a linear combination of the features, meaning they live in the span of these features. Okay, so that's like the first conclusion that we have. Any question? In addition, we have what Babish mentioned before, and is that the function can be expressed as its initial value plus some linear term and then what I mentioned before again, this is just the features. And so since we want this solution to interpolate the target function, then we have this linear system. This is just a vector representation. So this is essentially a matrix containing the features. This is the change in the parameters, and this is a vector containing the labels that we want to approximate. Okay, so these are the constraints. Then we have this. So this is like the second part. Now we have that the parameters live in an n-dimensional space, and we have a linear system of size n, because we have n examples, meaning that this solution is unique. There's a single point that that satisfies this linear equation. And in particular, if we consider some other...
Well,
Yeah.
that would depend on whether the matrix in the linear system is invertible or not.
It would depend on what, sorry?
But the matrix in the linear system is invertible. Is it singular or not? Like if it was singular, then we would be in trouble, right? You can't even solve this.
Yes, I guess that...
I think so, yeah. Because to have a unique solution, you need to have linear independence,
Uh-huh.
or like, yeah, you need to be.
Yes, I guess the assumption is that it is realizable. So there must exist an interpolator, no?
Yeah, from that, does it follow that this matrix is actually invertible? Because there were some approximations to get this matrix, right?
I guess that it not.
I
You
guess-
can use this pseudo inverse, and then for this to have an interpolator, that means that some of those rows would have to be zero at the same time that these ones are not. And actually, in the proof of one of these papers, that's the case. And they essentially remove those zeros because they cancel in both the matrix and in the target.
Right. Yeah. Right. If you don't have linear independence, you can still solve it. Maybe you will even have multiple solutions, right?
Uh-huh. And if we forget about this for a moment and we just think in possible solutions, then these vectors, like this essentially lives in R to the p times n. So actually this could have many solutions. So let's say that this, let's say this is a solution. That means we could, I'll just write like this. The solution, we're saying doesn't lie in this span, which means that we could represent it as, let's call this vector theta. This could be represented as some sum of something that lies in the span and something that doesn't. Which means that since this lives in a space orthogonal to this, the norm of this our solution is going to be it's going to be by triangle inequality larger than this. Sorry, equal. Which means that any other solution that satisfies the constraints that doesn't lie in this span is going to be higher in norm. And what we were saying is gradient descent will only find solutions that lie in this span. So gradient descent can only find the ones with minimum norm. Okay, and that's why we have like the first point, and is that gradient descent has a bias to find interpolators that satisfy the constraints, the linear constraints, and the solution found is the one that minimizes the norm. Okay. Any question?
I think we are kind of over time, Chava.
Yeah. Yeah, I think that we should finish here because then the other group won't have any time.
Yeah.
Sure.
I think we should wrap up, yeah.
Well, I guess you have to believe us that with the first one you get the second one, and the second one is just telling us the story that I mentioned before, and is that gradient descent will have a bias towards eigenvectors of the neural tangent kernel that have the highest eigenvalues, which in some cases translate to, for example, polynomials of minimum degree. Any questions, Sean?
I think I'm good.
Okay. Sorry.
So we're going to do a literature review for this project, and the topic that we have chosen is on gradient descent in.
I think Java definitely cannot see that. A bit large. Maybe you can write it a bit larger.
I definitely can't see it. Maybe you can move the computer to closer to wherever the action happens.
You can do
Yeah, the red is good.
So this is the topic that we have chosen. So the exact problem statement or the research question is, how do transformers or large language models learn in exhibit the in context learning behavior? So we know that if we give it some data set to in context, and we ask a query for it, it will give us a label according to that data set, and it seems to be working pretty well. So we want to know how does this happen in transformers, what kind of training dynamics are being involved, what kind of initializations are being involved, and how well the transformer can exhibit these behaviors by doing gradient descent in pre-training. So and the research question is, do transformers learn to implicitly perform GD for ICL? This is the research question that we want to look at, and there have been quite a lot of work done in the literature from 2022 to 2025, but we have chosen 3 representative papers of those work to discuss with you today. And we'll be doing that. But before that, let me just write the setup of those 3 papers. So let me just refresh the transformer block, especially the attention block in the transformers. Let's say this is the attention block with the inputs being matrix being Z. The attention block would be P times V times Z times G of Z transpose Q transpose K Z by rho Z. So this Z in an in-context learning case would be something like this, where we have example x1 and we wanted to predict y1, x2, y2, so on, xn, yn with n examples, and we have a query xn plus 1, and we wanted to predict yn plus 1, which is the ground truth. So this is the input matrix, and the attention block can be defined like this. where each xi is a d-dimensional vector and yi is a real number. And from this, the dimensions of, let me just write the dimensions of p, v, and q and k, where dh is the hidden dimension of the transformer and g is some function, g is some non-linearity or linearity. In usual transformers, this is the softmax function, right? And rho is another real number, just a scaling factor or normalization factor. So this is the usual attention block that we are familiar with. And in context learning tasks, this is kind of the input prompt that we give the transformer with n examples of data and labels, and we have a query data, and we want it to predict the ground truth for the query data. So this is the kind of setup for the transformer. And for the in-context learning tasks, we assume that each xi is coming from some distribution with some covariance sigma, and the yi is equal to some w star times xi inner product of these two vectors. Like w star is also an d-dimensional vector, and for each prompt, w star is coming from some other distribution like this. So this would be the setup for the in-context learning task, and this would be the attention block that we are looking at. Yeah, and the transformer is trying to solve this in-context learning task. So what would be the loss function that it would encounter? So is it okay if I erase this because this is clear? And the loss that is trying to minimize the L train is the summation of all the training examples of f attention of this minus y of n plus 1. We just take the bottom right element of the output of the attention matrix, attention block that it produces, and we have to we minimize the squared loss between this. This is the L prime that the attention block is trained on. So now that we have the basics of attention block and the in-context learning task setup and the objective that the transformer has to minimize, let's just discuss the 3 papers that we are going to see. With this setup, the three papers discuss that whether the transformers learn to implicitly perform GD to solve this ICL task. You can go ahead.
Is it visible? They don't explicitly do GD?
So this is implicit GD. So this loss is minimized by gradient descent, but whether the prediction of this yn plus 1 is being done using implicit GD by transformers, like the forward pass is a GD. Is that what that is what we're trying to see, whether the forward pass in the transformer is being equivalent to performing GD on this data set and giving us the W star or like yn plus 1.
Okay. Right. So we talked about the first paper, which is Transformers Learn in Context by Gradient Descent, there are 2 main questions. Number 1 is, what does one layer transformer really represent? And second is, what does the training really converge to? We'll mainly focus on this. So they proved that a single layer can actually implement one-step GD such that we define a step size matrix which is specific to the particular layer, where the sigma hat defines the covariance matrix, that is the relationship between your inputs, and G hat is actually the cross variance between labels. Over here, so we know that so these are your at the ith place, and this is how you define the laws. While the gradient when learned would be actually a relationship between your covariance matrix and the cross variance of labels. So if we are able to, if we choose our Q while selection of P is also scrutinized, we won't really talk about that. But if we choose our Q to be this, they prove in this paper that you can actually converge to this, which is learning gradient descent in a single setting, single layer setting. Moving on to the so this is also generalized to
There's a
actually
question.
yes.
Q is the block matrix with the zeros everywhere.
Yes. Q is the block matrix.
What's like the high level? Why does that work?
The dimensionality, you didn't define it.
No. Here, what is the dimension of A and other zeros?
Oh, okay. So
yeah. And what's the high level? Why does that work?
Okay, so what is really the objective of gradient descent is to reach the global minima. The global minima, at the global minima, you are actually able to replicate this in a single forward, in a single update. That is, it is solely dependent on the relationship between your inputs and the cross variance between your labels and the input that you have. While your activation could be actually defined as a learning step, you can. That's why I didn't really focus on this because that is specific to a setting.
Okay.
So yes, that's why.
Okay.
Make sense?
Yeah.
Right. They also right. And if we focus a bit on P, I mean, we still won't talk about the choice of P. It allows us to isolate these combinations, that is, these relationships, into the bottom coordinate for the query that you are passing on. So your output really, sorry, that's very dark. So your output for your query would actually support that, which again justifies that one step GD could be learned in a single layer setting. This can actually be extended to L layers, and they did that in subsequent terms. So the second work that we'll be talking about is that do we really follow
Wait.
the yes.
Can I have some questions here?
Yes, please. Sorry, so sorry.
You sped up quite a bit at the end. Like, what's the result? What's the claim? Is there a claim being made here?
So the claim is that this paper just tries to construct a set of weights for the attention block that that will implement one-step GD in
Right.
the forward pass.
So is it connected to the loss that you defined as
Yeah.
training loss?
Yeah,
That's
this is
on that.
connected to the training loss. So when we optimize the training loss with many examples of in-context learning data, we we can say that like this this loss could this kind of parameter settings that they construct could be achieved by minimizing the training loss. But this paper just tries to show that there exists a set of weights, but the subsequent paper tries to show that there is a training regime that can achieve that set of weights. Like they say that the global minimum represents those weights that have been constructed in this first paper.
I see. So first paper, it's not connecting it to the loss.
Yeah, it's not connecting it.
Second paper, it's starting to connect it to the loss.
Yeah, but in the first paper, they empirically show that the performance or the behavior that the transformer exhibits after training corresponds to one-step GD. They empirically show it, but they don't theoretically show it. The subsequent paper does.
Yeah. By the way, this whole topic is so weird, isn't it?
Yeah, I wanted to go into the motivation for why we are doing this as well, but the thing is, like, the main motivation is the mechanistic interpretability, right? Like, why is in-context learning is even being exhibited by studying the weights of the transformers.
I mean,
maybe
something is going to be exhibited. You can call it in-context learning, right?
Yeah.
Like a lot of times, I feel that like people give something a name and then it starts to live on its own as if that would have happened or something. It's like really forcing our views on these models of what they are doing and whatnot.
Yeah.
But I guess mechanistic interpretability actually asks the question whether this is actually happening or not.
Yeah.
Or like we want to make a hypothesis of like, is this actually happening? But I find this topic weird. It's also fascinating, but it's also very weird. It's because, of course, the models are never trained on doing any of these things. It's like this question was just asked because some people were thinking about it was the simplest example, I guess, for when the models could learn a learning algorithm and like what would be the simplest instance for that. But yeah, like why this algorithm and like why setting up things in this way and like just like what's the significance of getting an answer to this question too? It's like what does it tell us about how things work in the vibe? It's like I don't know, like why are we doing this? Like it's a lot of work.
Yeah, that is true. But some people also say that like this can be interpreted as like performing some kind of meta learning, which if we
Again, words, right? Like
yeah.
you can throw in more I don't know, human interpretations of what's happening.
Yeah.
And yeah, sure. It is in a way like good old fashioned meta learning. But now with transformers, if you wish, you can use this terminology. Right. It doesn't make it
Like tangible.
yeah, or like sometimes when like you ask a research question, you want to be able to either you're genuinely puzzled of like, is this possible to do or not? Like sometimes that's just the case. And sometimes you want to, I don't know, like make some connection to what's happening. But like here, I think it's so far removed from this transformers like in the discrete token world and like still like if you ask them to do this tasks, like they will reply something like that would fit the bill of gradient updates and linear regression or something, who knows how. But definitely not this way. It's like
Maybe in that case, like maybe we can interpret this to be testing the expressivity power of transformers because like we know that
right.
yeah,
Yeah.
We know the
Yeah.
transformers are
Like we
universal.
learn a little bit about that. Hey, like they can express these things, and if
Yeah.
they do express these things, then this
Yeah.
is how they do it.
Yeah.
And then on the top of it, hey, we can even learn these things.
Yeah. Yeah.
Even though no one is going to use SQL laws or anything like that, this transformers. But yeah, it's true. It just high level. I was curious about like what you think about this whole thing. All right, let's go on.
So yeah. So right. The second paper actually talks about the question: what does the optimal solution of training objective actually look like? And it also talks about the rate at which you actually reach the global minima. Is it optimal rate or is it not? Rate is actually a wrong word, but so these equations are all the same, but you actually see that there is an introduction of a precondition towards the sigma that was introduced earlier, and this precondition is related to actually related to that any global minimizer of the transformer training objective must implement the Bayes optimal linear estimator. So that says that if your activations are a combination of the eigenvalues of the relationship, some constant, and the number of samples that you have, the activation comes close to the relationship between inverse of the relationship between those training samples, and moreover, they actually also extend this to multiple layers. So for a 2-layer setup, which is just specific to that particular layer. But the thing actually is that so while over here the alpha I and beta I are just some set of scalars, and sorry, this is layer wise, and over here your updates would be looking like which are preconditioned to the set of scalars that are introduced for the matrix A of each layer. So all in all, this paper talks about the preconditioning of, so it's not just any arbitrary GD that is followed by a transformer when it is trying to learn a linear regression setup. Instead, it is the preconditioned GD, which is preconditioned towards the relationship between the between the set of training instances that it has. Do you want to talk about how it is related to loss?
Maybe you can go ahead. I think there's not a lot of time. It's not taking.
Okay.
Maybe you can wrap this up and then we'll talk about CO2.
Sure. So yeah, so the first paper talked about that we do learn, but is the solution really optimal or no? And this paper talks about the optimal solution of the training objective across n layer setup. We talked about 1 layer and 2 layers, which is dependent upon your eigenvalues and and the relationship between precondition towards the relationship between the training samples. Questions, please. No? Okay.
Do you guys have any questions?
I'm good.
Any questions? No?
So yeah, so far the two papers that we have discussed only talk about a single layer attention block with no MLPs and only one single layer attention. But now that what would happen if we introduce some kind of additional advantages for the training, like chain of thought maybe? What would the transformer learn to in this case? So let me just write it here. So while introducing chain of thought, the paper that I'm going to discuss right now modifies the in-context learning problem a little bit. Instead of predicting the label for the query, we have no query in this case, and we would like to predict the underlying linearity, underlying linear function that the data is being generated from. So in a way, we are trying to do in-context weight prediction for the linear regression task. So in this case, the data is represented as this. We have x1, y1, x2, y2, and so on up to xn, yn. Now we would like the model to predict this in a way, but we want to make it do it by chain of thought. So in the chain of thought case, it would be like this. It's the same x1, y1, x2, y2, so on to xn, yn, and we have the initial prediction of weight, and we have the one-step gradient descent, two-step gradient descent, so on up to k-step gradient descent. So we would like this is what a chain of thought prompt would look like. So we have the data, we have the initial prediction of how the data is coming, where the data is coming from, and in a similar fashion we have given the ground truth for each gradient descent step from this initial prediction of weight, and we wanted to predict the kth step gradient descent of the weight. So this is what a chain of thought data looks like, and the paper says that if we are using just a single layer linear attention block, linear being the G is linear, like it's an identity function kind of. So if you're using a single linear self-attention layer block without chain of thought data, this in-context weight prediction does not work and has the training loss to be of the order of, the evaluation loss to be of the order of d squared by n, where d is the dimensions of the input data and the n is the number of examples. And usually we can't have, and this error does go down as the number of in-context examples goes to infinity, but that is not the case. And similar, if you have limited number of samples, like let's say n is of the order of d, then in this case the error scales linearly with the number of dimensions of the data. So this is not a very good thing without chain of thought, but with chain of thought we can do it, and the paper says that the global minimum of the global minimum in the parameter space of the attention block with chain of thought can recover the weights, and will do it with an error of this order. So it is kind of good, like it is as the dimension scale, or and there are some other terms as well. So yeah, with chain of thought they can recover the underlying weight.
But this would be weird, right? Like if D gets larger, then things are getting easier. Why?
Because the number of chain of thought steps scale with the number dimensions.
So you, in a way, you have more data.
Yeah.
Why is it log?
For the chain of thought steps?
Yeah.
Not sure why that is low.
Who chose it?
It's the condition that is given in the theorem. Given that this is the case,
Can I make it b squared? Then it becomes even better? Or like, how does it work?
um,
Why not bigger? Why not smaller?
that, yeah, we have.
By the way, like, there is an n here somewhere, is there?
In
Number of
the,
examples?
in the last term, the bound for the last term, no.
So then, what's the meaning?
Like the majority of the, there are some logarithmic terms that are involved in the last term, again, along with the polynomial of d.
But what's this number? Like 1 over poly d, what does this number tell us? Invert.
Yeah, so
Like,
let,
this
let
is
me
the
just
number of
write the expression. I think
examples.
the expression contains the number of examples. Let me just go to that.
Surely it cannot be less than 1.
Mm. Yeah. Okay. So this expression is exactly 1 by d power c times 1 minus 1 by eta, where eta depends on the number of trying examples. So as the number of trying examples increases, as the number of trying examples increases, the error goes to 0, and as the dimension increases, the error goes to as the dimension increases, also error goes to 0, because the number of chain of thought steps goes to 0, because the number of gradient descent steps that we are asking it to predict goes to infinity. Do you want me to explain it again?
I'm talking to the muted microphone. Yeah, just give me a sec to start it. It's like I'm treating the log and then the x. So maybe that form is easier to understand. So there is d to the c times 1 over 1 minus eta, where eta is this n over n plus d plus 1. Is that right?
Yes. Yeah.
Okay. So if n goes to infinity, then the saying is that that goes to 1, then the 1 over 0 explodes. That becomes an infinity, and then you're improving. And otherwise, it's like in the exponential function of it's 1 over 1 minus eta n times log d. Okay, 1 over 1 minus eta, that's like 1 plus eta, or eta close to 0. But here eta goes to 1.
Yeah.
Oh, okay. What the heck?
No, maybe.
Okay.
C is just a constant.
Yeah, C is.
Yeah, subtract. Fine.
It's exponential in the.
Yeah, it's like.
That is because
Okay, it's actually much
forcing
easier,
it
right?
to-
Like if you write 1 over 1 minus eta, you expand it, then it's like n plus d plus 1 minus n. So that's d plus 1 in the denominator. and n in the denominator, so it's like n over d plus 1. Yeah, so now we have that and that in the exponent. So the claim is that this works as like exponential function of n over d plus 1 times log d. Okay, that makes more sense to me. So if you write it exponential function of,
I think I made a mistake. There should be log.
oh, you made a mistake.
There should be a logarithm here.
That is a log. Oh my god. Like
Now it's
all
linear.
our calculations are rude. But okay. It's just a log. I don't care. So then like it's exponential function of the log.
No, I think it's like log of
Yeah.
n.
Log of n, what
It's-
was it? N over d plus 1
When d is
Times.
high or like n is high.
log
Is high.
d,
When n
right?
is high, it will be just
So,
Yes.
one. Like,
and there is a negative sign. There must be a negative sign, otherwise, yeah, there is a negative sign. Yeah. So it's like, okay. So it's not plus, because you have the exponential function and a log. And then you have, okay, the log n over d plus 1, then just log n minus log d plus 1. And then you multiply the whole thing by log d. How does this work? So now you have exponential of minus log n times log d. Minus that's a plus log squared d. Okay, that's sort of I buy. So after simplification, you have this whole expression is the exponential function of minus log n times log d plus log squared d. In the exponent, you have minus log n log d, minus log n times log d plus log squared d. And if you think about it, and this is in the exponent, this is in the argument of the exponential function. So now if you're thinking about that, okay, like does big D have, to what degree does it have? If log D was not there, you didn't write it down, so you can't follow what I'm saying.
no, I'm just trying to see like.
Are you following what I'm saying?
I'm trying.
Okay,
to,
let me-
but,
Let me write it in the chat.
okay. Yeah.
I think maybe we can double check if that's correct. It's d to the c log 1 plus n over
I
n.
wrote it down.
Okay.
Just copy it. This is in the exponential function.
Okay. D c times log n log d minus log square d.
It's not minus, it's,
Oh.
okay. Because in the exponential function, there is no c, there is no d. It's in the argument of an exponential function. Get rid of the d. I don't know what the d is doing. Yeah, this is x of this. Yeah, e to the whole thing. Okay. So now you see that there is the log squared d term. That just makes you slow down. That's fine. Right? So that's like a e to the log d. That's like d, and then it's even to the log d. So that's like, oh, d to the log d. Fine. How about the other term?
This one.
So the other term, if there was no log d, it would be e to the minus log n. So that's like 1 over n. But that is the log d. Okay, what can we do with the log d? We can put it inside to the power of n. So it becomes 1 over n to the power of log d. So a bigger d is going to help you, but just mild this, right? Like it makes you a little bit faster. It's actually surprising. I don't really believe that this result is quite correct the way it is. It's,
I feel
it's
like
too
that is the
surprising
case
to me
because,
usually, like even with that, like you have more data or something. I don't know. Like this data is correlated, and like I don't know. Like it's like usually you don't see better than. Okay, so I guess maybe I take it back because I wanted to say in statistical learning, you don't see rates really below 1/√10. Okay, here there is no noise, so maybe you see something like, but it's just optimization. So you could see an exponential rate in it. Like if you have strongly convex smooth losses, then you can go with e to the minus n or something.
Yeah.
Although, wait for a second. This n is the number of examples. This is not what we optimize. So it's not an optimization error. Gosh, so you have an incomplete data set that you're trying to teach this thing that, okay, you learned gradient descent, but you present only this much data and data points.
And data
like
points
you-
and k gradient steps.
And then this extended with this log b.
Yeah.
Then, yeah. By the way, okay, so am I missing, is there an n on the board, like the length of the inputs is n?
This is.
So what's that index? What is that index?
This
Is it
index?
n?
Yeah, n.
Okay, so there is no number of examples here. It's just the length of the inputs,
Yes.
plus you add this log b.
Yeah, I mean.
So where is the number of
are, like,
examples?
examples are these, right? Like these are the examples.
So
there
it's just like, it's learning based on a single example. Like, just one example is this z is presented with this z of k.
yeah, this z
and
of
then-
k is a prompt with n examples, like x1.
Yeah. But like, how are the weights set? What are we talking about? We're talking about that you set up a loss function, and then you're adjusting the weights of the transformer
Yeah.
based on the loss. So into the loss, you put in a number of training points. I guess it was capital T before. Number of examples.
No, it was
Right?
n all the way. Like even here, we erased it, but yeah, it was n.
What was that for?
It was n.
But okay, so now I got confused because that was also n. This n is different. So let's call it capital T. That's what we would have. You don't see it, capital T. No. So that n can be n.
We talked about
And then-
examples in the previous one.
But the
Like
training.
this,
Okay.
this will be
Training.
just one input, like one example to learn from.
Oh yeah, this will be
So
one
are you
training
saying
data
that
point.
it's learning from a single example?
That's why this
No,
should be-
no,
this
oh,
should be
no,
T,
no.
this should be T.
No, this should be n, and there are like k such z case. Sorry, t such z case.
Okay, it has T copies of this.
Yeah.
And then it's just like in one example, if you have kind of more data, like a bigger M, bigger D means bigger chain of thought,
Hmm.
then you get this relationship, and we still don't see in this loss the T. It's like, what is the T? Number of training examples.
Oh, okay.
That's what I'm telling you.
No, I
Sure.
understand. Like I think this T also they talk about it because they have this T. Yeah. Yeah. So this T is of the order of log B plus log over 1 by epsilon. This 1 by epsilon is just to say that like this epsilon is the bound on the evaluation loss. Like the loss eval will be less than or equal after this many training examples.
Jeez, I forgot to mute myself. I had a hard time hearing what you say. Can you repeat that?
Okay, so let me just simplify this again. I don't think we need the log of 1 by epsilon. Maybe, yeah, okay, maybe we need it. So this is the number of training samples, the capital T. It's of the order of log
Okay, we want epsilon accuracy.
Yeah, we want epsilon.
We want epsilon accuracy,
Yeah.
is that right?
Yeah.
And what is the number that you were talking about before, the theta tilde number?
Theta tilde is the polynomial it's the loss function. So for any epsilon, so they say that this epsilon belongs from 1 over polynomial of d, like order of polynomial d to 1. So when you have this, so that's why they say it's the order of this, like the COT loss will be of the order of this, because the epsilon is always of the order of that.
So I'm sorry. I mute myself. Epsilon cannot be arbitrarily smaller, or like what's going on here?
Epsilon cannot be arbitrarily small. Like it is bounded between a function of d, which is like inverse of the polynomial, and 1. Like it is not as
That's very unexpected, right?
yeah.
Like I cannot say that like I'm going to drag the loss to 0, or like I'm going to make the situation arbitrarily better. There's a lower limit of how good the situation is going to be, and the only way to improve it further is to increase d. That's like, wow, that's surprising. Okay, but I still don't understand the theta tilde. Like, what does that number
This
represent?
number it just says that like this number represents the epsilon. Like it says that like the loss is less than or equal to epsilon, and the epsilon is of this order, right? Because we have this bound.
Oh, that's the same. That's the same. That's the
Yeah.
lower limit for epsilon.
Yeah, that's the lower limit for epsilon. Yeah, that's the same lower limit.
By the way, did you use little o there, or like big O, or that should be a theta?
In the paper, it is written big O. In the paper, it is written.
That seems to be wrong, but it should be theta, right? Because otherwise, it's like what is that? It's like anything smaller, like 0 is big O of that, right?
This is really big.
Yeah, it is.
0 is happily satisfying that. So it's like, I think that's theta. So, okay, then that would be the same thing as what you were talking about. And so that just means that the floor of the error can be pushed down if you make n bigger and d bigger in the specific way.
Yeah.
Okay. All right. Okay. Sorry, I totally didn't understand.
No, this is needed. Like I was trying to rush through things because we didn't have a lot of time, but this is needed. Yeah.
All right. Okay. Yeah. Yeah. I don't know whether it makes sense, but it's interesting for sure. Yeah. Like, do you think that there is a limit to what this can go with? Like, okay, you keep n fixed and d fixed, and it will not be learned, or will it be learned as t goes to infinity?
So, so you're saying as so there is there a value of d and such that we can't learn the gradient descent? Are you asking?
Or we can. Oh, maybe we can. I don't know. Like, it's like, I don't know. But this paper is not saying you can. It's saying that there is an absolute, like, we don't know whether you can go beyond this absolute limit, which looks like, okay, not so bad, but it's an arbitrary limit as far as I'm concerned. It's like, it's unexpected that it says that, like, is it, I would think that that's an artifact of the proof.
Yeah, it is. It seems like we can't arbitrarily decrease the loss as much as we want because it is.
Exactly.
Yeah. It seems like that.
Like, it could be if there is a capacity limit, for example, but the capacity doesn't change just because you are making sequences longer.
Yeah.
It's the same capacity, so it's like, okay, what's somehow there is more information though if you're making the sequences longer.
Mm-hmm.
It's true.
Yeah.
Yeah. All right. Okay.
This is interesting. Yeah. Maybe that can be a future work for this literature from this literature.
And absolutely. Other interesting question: if k is made bigger, they say 2d log d, but if I want to make gradient descent converge, and it's a d-dimensional problem, how many steps do I need to make? Well, it's usually scarce with d, linearly, not with log D. So,
Yeah.
so then, like, would the theory not go through if you try something like that?
Yeah.
Also, did these guys run experiments, by the way?
They did, but not. They have some kind of heat maps of the attention parameters that they learn, but not the curves. Oh yeah.
Right. Because I'm wondering whether it actually works at all.
No, they change. They say that like as K increases, the loss gets better and better, and we do better than without COT.
These are super interesting questions. You can study theoretically, empirically, see whether, like their theory, like why does it break when K is log B? All right. Anyways, we're beyond log. I guess we have to let everyone go. Maybe everyone already left.
One question.
Thanks so
Yes.
much.
Some left, some are still here. There's a question actually.
Do
Oh, yeah,
do
okay.
do they do any relationship with reasoning? Because this is like providing case steps, and then
Yeah.
you can interpret this as
They
intermediate steps.
They have listed it in terms in future works, saying can we interpret this as reasoning, because we are asking it to predict the intermediary steps as well, and we're just trying to see whether the final answer is right or not. The loss only depends on the final answer, right? So yeah, they are trying to see whether this is kind of how we can build reasoning in transformers.
I see.
They haven't extended it to language tasks or any reasoning tasks, and they listed it in future works. Yeah. So yeah, that could be one future work, and another future work is to like see what is the effect of K. What if we increase the K to theta of D or like theta of D square? What if we ask it to predict more and more reasoning steps? Maybe it could diverge, right? Like because if we ask it to predict more and more intermediary steps, the error propagates through the intermediary steps, maybe because it is being autoregressively fed through all these things. Like not autoregressive, but maybe the terminology is wrong. But maybe if we ask it to predict more and more intermediary steps, it may diverge, right? Like, is that why they chose log D? Maybe.
So as K increases,
Yeah, as K increases.
as K increases, yeah.
It may diverge, like it may diverge from the
Yes.
predict W star, right? Like,
Yeah. It should.
is that what? Is that maybe a possibility, Chava?
You're on mute.
You're on mute.
What is the possibility?
Because if K increases, we are asking it to like produce more and more steps, right? Like intermediary steps.
Yeah.
That may lead for some kind of divergence in terms of the error propagates through these intermediary steps.
Right. It depends on how you do the training. If you do teacher forcing and whatnot, then the error propagation it's not bad at all.
Okay. So the teacher forcing means that like we want it to get it right at
You
every
provide-
point of step.
Right, you provide the correct inputs, and then even if the model starts to predict something else, you don't expect it to, like punish it for just the one-step errors. They're punished for the one-step errors. The model is always trained to minimize one-step error, not multi-step error.
Okay.
There's no multi-step error minimization. Multi-step error minimization is kind of hard. And if you do the one-step thing, if you have many steps, it just helps. It's just like how would that make things worse?
Okay. Then maybe.
And I assume that these guys are doing feature forcing. Like they're doing the one-step errors.
Okay. Yeah, that makes sense. Yeah.
All right, okay. Interesting.